In this video, we are going to finish looking at polar equations and how to rewrite equations from polar coordinates to rectangular coordinates. To do so, recall that if we know a point P has rectangular coordinates xy and polar coordinates r theta, then the relationship between them is that x can be always written as r cosine of theta, and y can be written as r sine of theta. And since this is a right triangle, we know by the Pythagorean theorem x squared plus y squared is r squared. And because it's a right triangle, we know that the tangent of theta is this ratio y divided by x. Let's use these tools to see if we can rewrite some equations in polar coordinates to rectangular coordinates. Converting equations from the polar coordinate system to the rectangular coordinate system is not as straightforward as the other way around. We still look to use our common substitutions when possible, though. Well, let's look at our first example, r equals 3. And to get this equation in its rectangular coordinate form, we could maybe square both sides. Of course, this will give us r squared is 9. And since we know that r squared is the same as x squared plus y squared, we have x squared plus y squared is 9. And so this would be the rectangular coordinate description of r equals 3. Now let's look at theta equals 4 pi over 3. And recall that 4 pi over 3 is an angle on the unit circle that lives in the third quadrant. It would be an angle in this direction. To rewrite this angle theta equals 4 pi over 3 in terms of the rectangular coordinate system, we're going to take the tangent of each side. So we have the tangent of theta, the left side, we have to equal the tangent of 4 pi over 3. But the tangent of 4 pi over 3 we know is square root of 3. So this tells us the tangent of theta is square root of 3. But we also know that the tangent of theta can be written as y divided by x. So that we have from these two portions here that root 3 is y over x, multiply both sides by x, and we have y is equal to square root of 3x. Note that this is a straight line with slope of root 3. So up here, if we have theta as 4 pi over 3, then y equals root 3x would describe the same line as theta equals 4 pi over 3. Let's look at two more examples of converting equations from polar coordinates to rectangular coordinates using some substitutions that we know. To rewrite the equation r equals 2 cosine theta in rectangular coordinates, we might multiply both sides of this equation by r. Of course, this would introduce the term r squared equals, and this right-hand side, let's write it as 2r cosine of theta. Of course, we'll substitute r squared with x squared plus y squared. And we'll substitute the r cosine of theta with an x. This is now an implicit equation of y and x, but we're going to try and rewrite this in a more standard form. By maybe bringing this 2x to the left-hand side, we can write this as x squared minus 2x plus y squared equals 0. Recall that if we were to complete the square on x, we should be able to write this in a more standard form of a circle. To complete the square, remember you take half of that middle term and you square it. This will give us negative 2 divided by 2 is 1. Negative 1 squared is positive 1. Adding 1 to both sides to keep equality. This now allows us to write these first three terms as x minus 1 squared plus y squared equals 1, which we do recognize as a circle of radius 1 that's been shifted 1 unit to the right. So it would be centered at 1, 0. Our circle would look something like this. Let's look at our next example. R equals 1 minus cosine of theta. To write this equation in its rectangular coordinate form, let's again multiply both sides by r. Now this would give us on the left-hand side r squared equals r minus r cosine of theta. To rewrite this, let's now bring this r cosine of theta to the right-hand side. And so we would have r squared plus r cosine of theta equals r. The r squared, we know how to take care of that. The r cosine of theta, we know how to address this. But this extra factor of r over here, or this r term over here, we're not sure what to do with this just yet. So again, we imagine squaring both sides of our equation. This would give us on the left-hand side r squared, which we know of as it's x squared plus y squared. R cosine of theta, we know that as x. And then on the right-hand side, the r squared that we have, we again know is x squared plus y squared. I don't recognize what this equation is in the xy plane, or in the rectangular coordinate system, but it is an equation in the rectangular coordinate system. Let's look at just two more examples. For our last two examples, let's convert each of these equations from polar coordinates to rectangular coordinates. Now let's look at r equals 7 secant of theta. To get this in a more familiar form, remember that we can write this as r equals 7 divided by, now secant of theta is the same as 1 over the cosine of theta. Multiplying both sides by cosine, we have r cosine of theta is 7. Recall our familiar substitution, r cosine of theta, that's really x. So we see that x equals 7 is the rectangular coordinate version of 7 secant theta. Let's try one last one over here. R equals 2 secant theta tangent theta. And again, think as rewriting these in terms of sine and cosine, this could be r equals 2 times 1 over the cosine of theta times the tangent of theta. Multiply both sides of our equation by cosine, we would have r cosine of theta is 2 tangent of theta. Of course, r cosine theta we recognize as x, and 2 tangent theta, well, at least tangent of theta, you think of as y divided by x. Multiplying both sides of this equation by x, we would come up with x squared equals 2y. And we recognize this as the equation of a parabola in the rectangular coordinate system. I hope this video was helpful, and I will see you guys next time.